Okay, keeping with our new high production standards, we will start exactly at 4 o'clock. It is my pleasure to introduce Jennifer Yee, who I think needs almost no introduction, but there are formalities. Jennifer was an undergraduate at Swarthmore, went on to OSU and studied with Andy Gould. You came to us 3.5 years ago, and as a Sagan Fellow. Let's see, what else? She's one of the most recent additions to the federal staff at the Smithsonian. She is leading the reduction pipeline for the KMT network of telescopes. You're going to talk about that. So I hope, so I won't. And is also on the W1st Science Implementation Team. Now, just to put this in context, if OSU and CFA were football teams, the way you would see this is we traded Kachanik, Stanek, Martini, and Gowdy for Jennifer. You are a very valuable player. So without further ado, Jennifer.
Okay, well, thank you. Thank you. I'm pleased today to introduce you, if you haven't already heard, to my research on microlensing. And so to start out, I would like to start with this quote from Albert Einstein, which says, "Even in the most favorable cases, there is no great chance of observing this phenomenon."
He said the same thing about gravitational waves.
Okay, well, Einstein was right about a great many things. Apparently also wrong about gravitational waves. In this case, I'm proposing to talk to you for about 45 minutes about observational microlensing. So we might wonder why Einstein was so wrong about this. And so to start out with thinking about that, we should think about the physics of microlensing. So in microlensing, we have a lens mass, and then we have us. And we look out through the galaxy and we see a source star in projection behind this lens mass, and the light from that source star gets bent and split into multiple images. And so this is the face-on view of that. We've got the lens, the far distant background source, the images of the source, and the Einstein ring. And so the Einstein ring sets the fundamental scale of microlensing. And if we're talking about stellar lensing, two stars within our own galaxy, the scale of this, the Einstein ring, has a radius of about 1 milliarcsecond. And so in order to observe microlensing at all, you need two stars that kiloparsecs apart from each other, doing their own thing in the galaxy, to have a chance conjunction that's better than 1 milliarcsecond. And so the answer is that Einstein wasn't wrong. There is no great chance of observing this phenomenon. And what's changed since 1936 is that we have CCDs now. And so this is the Ogle 4 camera. It's got 32 CCDs. This is a single pointing of that camera, field 505. And if you observe 1 million stars towards the bulge, then you will get one microlensing event. And so you can see there are oodles of stars here. And there are about 150 microlensing events that were observed the entire 2016 microlensing season in this field. So only 116 of these tiny pixels were actually microlensed. And so Einstein wasn't wrong. It's a hard problem. The first microlensing events were discovered in 92, published in 93. And so this is the first microlensing event that was observed by the MACHO collaboration. We have two different panels here, one showing the event in the blue and one in the red. And so you see the magnification as a function of time. And what you see in these two panels is you see the same microlensing event in both panels. And so because the form of this signal is the same, that's confirmation that this is microlensing, because microlensing is achromatic. The timescale of this event is about 17 days in the way that we formulate timescale now. And It's a beautiful event. The difference is that in 1993, CCDs are much smaller than they are today. The whole cameras were smaller. And so we're seeing a cadence of about once per day, once per night, of this event, which is perfectly acceptable to resolve this stellar microlensing event. By 1993, we were seeing the first binary star microlensing events. And this event, which is Ogle 7, has a very classic double-horned structure. And so you get these two beautiful caustic crossings that indicate that this is a binary star event. But if you look at these caustic crossings in detail, what you see is that this cadence of once per night is insufficient to resolve this structure of that caustic crossing. In addition to that, it was realized that microlensing could be used to find planetary signals. And so in Gould and Loeb, they estimated what a microlensing planet would look like. And the timescale of that microlensing planet is much shorter than the timescale of the underlying stellar event. And so the timescale of the planet scales as the square root of the planet mass. And so if your typical stellar event is 20 days, then your typical Jupiter mass planetary event is only 1 day. If your mass is smaller, the timescale is even shorter. And so clearly, a cadence of once per night is not sufficient to resolve caustic crossings or to resolve these planetary signals from microlensing events. And so Gould and Loeb advocated a two-phase approach. First, you would have survey groups. And so when I was a graduate student, the two big survey groups were the MOA collaboration and the Ogle collaboration. And then you would have a network of telescopes to follow up specific microlensing events. And so I ran the Microfund network, which has about a dozen active members, and they're spread all over the globe, but especially concentrated in New Zealand, which is a hotbed of amateur astronomy. And then we have the question, though, which events should we follow up? Hundreds of microlensing events are observed every year. And so once you've found these events, which ones deserve high cadence follow-up observations? Right? In our case, we were working with amateurs, so we had this added problem that, they had day jobs, and so they couldn't dedicate all of their time to observing these events. So we had to pick some of our favorites. So how do you decide that? Well, let's look again at the geometry of microlensing. All right. If you have a lens star, you can calculate the magnification pattern due to that lens at any point in space. And so in this case, we have a single star, and then we have a source star, and that source traces a path across this magnification pattern, which produces the microlensing event we see. And the closer the source gets to the lens star, the brighter that microlensing event is. If you add a planet around the lens star, you perturb this map. And in these places highlighted in red, the perturbations are so strong that the magnification pattern formally diverges to infinity. And those places are called the caustics. And so if you have a source that crosses over that caustic, you'll get an additional perturbation from the planet, and you can detect the planet. So in this diagram, I'm going to highlight this for you because it's hard to see. There's actually two sets of caustics. There are planetary caustics and there are central caustics. And the planetary caustics are on the left, and you can see they have a very large cross-section. And so the expectation at the time of Gould and Loeb was that most planetary events should come from planetary caustic crossings, because that's where the cross-section is largest. The problem with planetary caustics is that you can't predict when that perturbation is going to occur. And so you could have a source, and if it crosses like that, then you get the perturbation at the beginning of the microlensing event. But the source has nothing to do with the lens, and so it's just doing its own thing, and it could just as well go the other way. And then you have the planetary perturbation at the end of the microlensing event instead of the beginning. Or the source could just go over here, and then you get no planet. And so in order to observe planetary caustic crossings well, you have to observe as many events as possible, preferably all events, at a very high cadence. And so that doesn't actually help us. But if you consider the central caustic, that central caustic always shows up at the position of the lens star. And so if you can predict a microlensing event, and you can predict that it will be highly magnified, then you know that the source star must pass very close to the lens, and therefore, regardless of what orientation it's in, it should produce a planetary signal if there is a planet to detect. It also has the added advantage that you know the central caustic is at the position of the lens star, so that perturbation must occur when the event is most highly magnified. So it should occur over the peak of the event. And now you've narrowed yourself down to just a few events that you want to observe, and you've got a very tight time window when you want to observe them, and everything's good. So in practice, this works like this. So it's the 4th of July, 2011. We get an alert from MOAA that says, new microlensing event, MOAA 2011 bulge 293. And I fit this event, and I see that it's going to peak at very high magnification in less than 12 hours. And so we must start observing this event as soon as possible. And so you send out the emails, you send out the Twitter, which says, MB 293 peak at UT1, AMAX greater than 270 at 1 sigma. Africa and South America will see the peak. Israel will see the rise. Strong sensitivity to planets. Observations are urgently needed. Okay, all right. And then you start planning your observations from Chile. And so there's this 10-hour time window when you can see the data from Chile. And then you sit and you wait, and the sun goes down, and you wait, and you wait, and you watch, and you see these data. And this event dropped half a magnitude in the first 20 minutes we observed it, which is completely inconsistent with the model, but very consistent with a caustic exit. And so we're seeing an anomaly, a perturbation that could be due to a planet. And so then you get more emails, and you call the observer at CTIO on Skype, and you say, please, take more observations. And then observations are taken, and the sun rises, and you get this beautiful microlensing event where you have this double bump structure. There's a caustic exit right where those 4 data points were taken. And from that, you see a planet, and it has a mass ratio of 5 times 10 to the minus 3, making it a super Jupiter. Great, it's a planet. Well, then you do it again. Now it's March 2012. Events, you fit them. Oh my gosh, Twitter, emails, Twitter, emails. Oh, it's anomalous. More Twitter, special Twitter emergency, tweeting. Anyways, and then you combine data from all these observations, all these observatories, and you see beautiful signals. And here we found actually the second 2-planet system with microlensing. You have one planet here, and then another planet with the dip there. And they have mass ratios of sort of 10 to the minus 4, or they're both about 10 to the minus 3. And so they're both gas giants. And so we have these 2 beautiful planetary signals. Oof. But you can see there's a problem with this method, right? The first one is that it's crazy. It requires 2 hours of my time every day continuously from mid-March to mid-October. No vacations, right? That first planet we found was the 4th of July planet. If I took vacation, we would have missed one of the 6 planets that were found that year. The second problem with this method is that we're missing most of the planets. High magnification events account for less than 1% of all microlensing events observed every year. And the central caustic is very small. If you have that kind of event, it's very likely you will find the planet, but most of the planets are not actually central caustic planets. Most of them are planetary caustic planets. The problem, up to that point, was that we couldn't observe all microlensing events equally. And so the solution to this problem is KMT-net. And so I've been working on KMT-net with 2 postdocs here, Ingu Shin and Yoon-Kil Jung. And the way that KMT-net works is they have the biggest camera that you can get. It's 2 degrees on a side. It's got 4 different chips. We have the Pleiades and the moon shown here for scale. So it's a big camera. And so the idea is to observe as large an area as possible, get those millions of stars that you need to detect microlensing events, but also get them at a cadence where you can characterize planetary perturbations. And so KMT-net has 3 fields that have a 15-minute cadence, which is good enough to detect Earth mass planets. It has another 7 fields where we have a 1-hour cadence, which will get us Neptune mass planets. And then 12 more fields that have a 2.5-hour cadence, which gets you to progressively larger planets. And then 5-hour fields, of which there are 3, which get you Jupiter mass planets. So we're covering an enormous area of the sky at this very high cadence to detect planetary perturbations. In addition to that, KMT-net has 3 different sites. And so we can observe microlensing events continuously, weather permitting, with these very high cadences. And so KMT was commissioned in 2015. This is an event that Ingu analyzed. And so you can see beautiful 40-day underlying stellar microlensing event But on top of that, you have this perturbation, which he found was caused by a planet with a mass ratio of 10 to the minus 2, which makes it another super Jupiter type planet. But if you look in detail at this caustic crossing, you can see that there are 3 KMT net points that are resolving this caustic entrance. Because of this very high cadence and very wide field, we're able to capture microlensing phenomena at many different timescales. We have the 30-minute caustic crossing, we have a 12-hour planetary event, and then we have the 40-day timescale of the underlying stellar event. Now, we have another problem, which is that mass ratio is not the same thing as planet mass. Up to now, I've only quoted to you mass ratios because that is the fundamental microlensing observable. But there are people who care about what the true mass of the planet is. And so if you want to know that, though, to get from mass ratio to true planet mass, you must figure out the mass of your host star. But microlensing has a major problem with that, because here you see in the center of the slide a beautiful microlensing event, super bright, lots of photons. All of those photons come from the source star. It's from the background source. At baseline, when there's no source light, you see nothing. So you're not detecting light from that host star. So what do? Well, it turns out you can measure higher order microlensing effects. And then you have a simple equation. The mass of the star is equal to the angular size of the Einstein ring divided by the microlens parallax times a constant. So constants are known, so that's good. The angular size of the Einstein ring we get in most events with caustic crossings. And so the question really is, how do we measure microlens parallax? And so I've been working with the Spitzer Space Telescope to actually measure microlens parallax. And so this effect relies on the fact that what you're seeing in microlensing is you're seeing the conjunction of 2 stars, and your own particular perspective matters. So this is the same thing when you go to the eye doctor and they say, look at the doorknob, put your hand over your left eye, all right, now then switch, and the doorknob moves. That is the parallax effect that we see, right? So in this case, the doorknob is the lens, and then the background is the source. And you're switching eyeballs. So you have Earth and Spitzer. And so if you observe the same microlensing event from these 2 different locations, you should see a different microlensing light curve. And so this idea actually goes all the way back to Refstel in the 60s. But it wasn't until 2014 that we actually started measuring this. And so you can see we have a beautiful light curve from Ogle and a beautiful light curve from Spitzer. And there's a difference in the heights of these 2 light curves, a difference in their timing, in the timing of that peak. And this is caused by the parallax effect. And by measuring that parallax effect, we can tell that this lens star is an M dwarf at 3 kiloparsecs. Pretty cool. In practice, the Spitzer campaign works a lot like follow-up of high magnification events. You see an event, you think it's good, you select it for observations with Spitzer. Normally with Spitzer, if you've ever submitted Spitzer observations, they tell you, all right, your targets are due 6 weeks before your observations start. So 6 weeks is like 45 days? Given that the timescale of microlensing is only about 20 days, that's not actually, that's a serious problem. And so we worked out with Spitzer operations a special deal. We send them our final target list Monday morning. They get uploaded on Wednesday, and the observations start on Thursday. And so we pick this target, seems good, upload it on a Monday, observations start Thursday. We just say, keep observing it, we'll keep observing it, yep, okay, we'll keep observing. Oh, planet! So then you get planet, and it's great. And in the end, you get this beautiful light curve. And again, the black is the Ogle light curve, and the red is Spitzer. And the amazing thing about this event is that Spitzer sees the same event, but offset 20 days earlier. And they see the same planetary perturbation that you see from the ground. And this 20-day offset comes from the parallax effect. And so based on this, we determine that this is another giant planet, and it's orbiting a K-dwarf. And so the 2014 Spitzer microlensing season was the pilot season. And based on that, we learned a lot about how microlensing works. We proved that you could observe it. And at that point, things got really intense. And actually, it got so intense that after the 2015 season, Spitzer operations immortalized this event in a t-shirt. And so one of the things that changed was that we started thinking about what we measured, right? Our whole goal was we want to measure parallax so we can measure masses of planets. We want to measure parallax so we can measure masses of planets. We're measuring parallax. Parallax. What do normal people use parallax to measure? Distance, right? Distance. So if we're measuring parallax, we can measure distance. So now we can look at the distances of these planetary systems in our galaxy and ask how they change in different environments. And so in 2015, we revamped the whole Spitzer program with this idea in mind, and we made it a much more rigorous experiment. And we saw this beautiful light curve of a microlensing planet. And so you got the planetary perturbation. If you measure the width of that planetary perturbation, that's where you get the theta E from. Right? And so that's half of the information you need to measure masses. You see the ground-based light curve and the Spitzer light curve, which in this case is in purple, and you see the beautiful parallax effect. And from that, you can measure the mass. But to get distance, you need another piece of information. You need to know where your source star is. Now, in general, the source is in the bulge. And you can just assume that it's in the bulge. And if you make a CMD, you can confirm that the source star is in the bulge. Because most of the stars in these fields are towards the bulge, right? So if you have a CMD, you have the red circle shows the centroid of the red clump, which are all giants in the bulge. And so the bulge stars are all at similar colors. And then the disk stars are the sequence off to the left, right? And so normally you can see that it's very clear. The sources all show up in the bulge circle, and it's all in the bulge, and everybody's happy. In this case, the source is right here, right smack between the two populations. And so there's an ambiguity. Is it in the disk? Is it in the bulge? Is it at 4 kiloparsecs? Is it at 8 kiloparsecs? And so I actually took a spectrum of this object with Mike while it was still magnified to determine the radial velocity of this source star. And so this is work that I did with Sam Johnson, who actually measured the radial velocity. And so he was here doing Minerva, and now he's gone on to graduate school at Ohio State. And the gray is the Mike spectrum. The blue and the red are models from Phoenix, or Phoenix spectral models. And if you look at the lines, you see there's a slight offset in those lines. And the spectrum is slightly redshifted. And so Sam, did a full numerical fit and quantified all of this. And he found that the source is moving away from us at 50 kilometers per second. And this is a somewhat disappointing result, because the velocity dispersion of the disk is 30 kilometers per second, and the velocity dispersion of the bulge is 100 kilometers per second. So if we had measured 100 kilometers per second, we could say it's in the bulge. But with only 50 kilometers per second, we could say, well, it's kind of still ambiguous. But in this case, well, in all cases, there are more stars in the bulge than there are on the disk. And so it's most likely in the bulge just because they're 4 times more abundant. So if we use that assumption that the source is in the bulge at 8 kiloparsecs, then we can make a relationship between the lens star mass and the distance. And so based on parallax, we get the blue line, that measurement of pi e from Spitzer. Based on the measurement of theta e from the width of the planetary perturbation, we get the red line, and then they have a very nice intersection, very clear intersection. And so we find out that this system is about a little over 3 kiloparsecs away. The planet is 20 Earth masses. It's around an M dwarf with a separation of about 3 AU. And so this is a beautiful detection of the distance to a planetary system. The other thing, though, that changed in 2015 is that KMT started. And so the combination of KMTnet and Spitzer is incredibly powerful. And so in total, there were 50 OGLE events that were observed by Spitzer that were also in the KMTnet prime fields. And so you see the black data here are all from OGLE, the red data are from Spitzer, lots of clear, beautiful parallax detections, but no planets. And even though there are no planets, though, we can still place constraints on the occurrence rate of planets. So if we look at this in detail, right, we've got 2 example events, OGLE 987 and OGLE 1189. And this is what they look like with just the OGLE data. And so you might imagine, well, maybe there's a planet like hiding here that we just don't resolve, with these ogle data. But when you add the KMT-net data, you see the incredible power of these data in filling in the light curves, the having multiple sites, which helps compensate a lot for weather, just the density of the data. And so we have incredible sensitivity to planets in these events, even though we don't detect them. And so these two events were analyzed by Young-Kil, who figured out the detection efficiencies for them. And so these plots show the detection efficiency. So if from left to right you have increasing planet mass, and then each of these squares shows, if there's a planet at this location and it's colored in, that means you could detect a planet there. And so the first thing that you see is that you're most sensitive to planets near the Einstein ring. You get this very round circular feature. You also see very clearly that you're more sensitive to planets that are larger, which makes sense. But you see there's actually a real difference between the planet in the bottom and the diagram in the top. The diagram in the top has these funny white cutouts. There's like chunks missing from it, which is weird maybe because the light curves seem to have even coverage. And so the difference between these two events is the way that they were selected for observations with Spitzer. And so 1189 was selected based on objective criteria. So before the 2015 season, we laid out a bunch of criteria and said, well, if an event meets these criteria, we just want to observe it. We definitely 100% want to observe it. And so if we observe all of those events, then those form a clearly objective sample, and we can easily measure planet sensitivity and planet occurrence rate from that sample. And so this bottom event was selected in that way. The problem is we didn't understand completely all events that might be good targets with Spitzer. And so we also wanted to reserve the right to just pick a target because we thought it would be good for measuring a Spitzer parallax. And so the top event, 987, was selected in this subjective manner. So we decided pretty near the peak that we think we can measure parallax with this from Spitzer. It seems pretty good. We want to do it. But a human is now involved in this decision. And so to keep your sample pure, we have to eliminate all of the light curve that happens before that peak, because that, if there was a planet there, we would have seen it, and that might have influenced our decision as to whether or not to observe this event with Spitzer. And so these two events just represent different selection criteria with Spitzer, or different methods of selection. And so those white gaps are places where planets in those gaps would have been in the excluded part of the light curve. And so those are eliminated. And so in total, there were 50 events observed by Ogle, Spitzer, and KMT. And 9 of those did not have good parallax measurements, so we threw those away. The other 41 we split up. Half of them were analyzed here by Ingu and Young-Kil, and the other half were analyzed at CASI, which is the Korea Astronomy and Space Science Institute, and they're partners with us in working on KMT. And when all of these detection efficiencies were done, you can combine them into a master plot that shows mass ratio versus separation, and then the fraction of planets that you expect to detect at each combination of those parameters. And so again, it shows you its biggest, it peaks at a log S of 0, which is at the Einstein ring. And it goes all the way down in mass ratios to 10 to the minus 4, but most of the sensitivity is towards larger mass planets. And so we have a lot of sensitivity to gas giant planets with this. And so from that, we can then place constraints on what the occurrence rate of planets is. And so this shows number of planets per star per deck squared as a function of the slope of the mass function. And so previously, we had this measurement from Gould et al. 2010 based on the high magnification events that I showed earlier, the survey plus follow-up strategy. And so they found that about 1/3, there should be 0.3 planets per star per deck squared, if assuming that the mass function is flat. And in this case, we don't have a measurement because we don't have any planets in this sample of 41 events, but we can place constraints on it. And the 2 sigma limit for a flat mass function is that it's less than half. And so these measurements are consistent. But it shows you where this is going as we collect more events with Spitzer parallaxes. Another thing that we're learning from this sample is that we can look at the cumulative distribution of events and sensitivities as a function of distance. And so what you see here is you focus on the bulge populations and the disk populations. And what you see is that about 30% of these objects are coming from the bulge. And so if the frequency of planets in the disk is the same as the frequency of planets in the bulge, then you expect, one bulge planet for every 2 disk planets. And so when we actually detect planets, they should be split up in this ratio if the frequencies are the same. And any deviation from this 2-to-1 measurement, or 2-to-1 expectation, indicates that the actual distributions are different. The combination of KMT-net and Spitzer has implications, though, also beyond planets. And so, for example, we have this 2015 event that Ingu analyzed, and you can see it's got the classic binary microlensing feature, right? So it's a stellar binary. It has beautifully resolved caustic crossings due to the KMT-net data. And Ingu analyzed this, and he found that it is an equal mass stellar binary. And so you might wonder, well, why should we care about stellar binaries? I mean, there are lots of people who do care about stellar binaries, but generally, when they care about them, they want to know things. They want to know things like, what are the masses of the components? What are their orbital elements? Maybe what are the radii? What are the colors and the magnitudes? And, to first order in microlensing, we get mass ratio. Mass ratio is 1. So that's not a terribly useful measurement by itself. But this event also has an interesting feature that there's greater than 50 days between these 2 caustic crossings, which means that we're able to measure higher order effects. So Ingu modeled this, and he measured it including the effects of parallax and orbital motion. And so if you look at this picture showing the geometry of the event, this black line here shows the trajectory of the source. And it's not a straight line. It's very curved. And that curvature in the source trajectory is due to the projection of the Earth's orbit onto this event. So you're seeing the effect of the Earth moving during the course of the observations. In addition to that, you see this caustic structure. This is the caustic at the time of the first caustic entrance. Over the course of the event, that caustic is rotating and changing shape. And that's due to the orbital motion of the lens star. And so by combining these 2 effects of parallax and orbital motion, Ingu's able to find out, well, it's not just equal mass. It's an M-dwarf binary with a separation of about 2.5 AU. And it's at 1.5 kiloparsecs, so you'll never measure anything else about it. So again, why should you care? Well, these effects, because we measure these effects, we actually know that we have Spitzer data on this event. And from this measurement, Ingu's modeling of the event, he showed that there are actually 2 models, 2 degenerate models for this light curve. We know that parallax and orbital motion are somewhat degenerate with each other because they're both, it's the orbit of the lens versus the orbit of the Earth, and those 2 things are going to be related. And you might wonder, well, what's the point of that? Like, do you actually measure that? Like, I show you this light curve, and you'll believe me when I tell you there's more than one body there. If I tell you I also measure orbital motion and the motion of the Earth projected in this light curve, it's a little harder to tell. But with these effects, Ingu was able to predict what the source trajectory should be as seen from Spitzer, and therefore predict what the Spitzer light curve should be. And so we do have this beautiful Spitzer light curve. These are the Spitzer data here. You can see there, it's just a small fragment of the light curve, and it's very weak. It's a very small signal. And so you might actually wonder, well, can you actually learn anything from such a small piece of the light curve? And the answer is yes. So the red line here shows the prediction of what that light curve should look like based on the ground-based data. And the purple line shows the data, the real data and the fit to those real data. And so on the left, we see that the one model is clearly confirmed by the Spitzer data. And on the right, we see that the model is ruled out. So it works great. And so KMT has really changed the Spitzer program. And the combination of the 2 are incredibly powerful. In addition to that, as we're exploring KMT data, we're finding new phenomena. And so this is an event from this year. Jungiel found this in the Ogle alerts, Ogle 10 or 0733, and you can see that it's clearly anomalous. It's not a point lens. And our goal is to find planets. So the first thing he does is he fits it with a planet model. He finds a beautiful planet model where the source is traveling directly along the star-planet axis. And this part of the source trajectory, where it's crossing over all of these beautiful caustic structures, corresponds to this part of the light curve. And you can see in this part of the light curve that the model is quite wiggly, and that's because of the caustic structures. But if you look closely at it, you see that the data are straight. So that's quite odd. And so Jungiel searched for a new model, and he found a much better model that fits the data significantly better, is smooth in this region. And in this case, what it corresponds to is a single lens star, no planets, oops, and with two different sources. And so you get these two, what you're seeing is two different microlensing events superposed on each other, corresponding to the same lens star. And that's actually quite important because we're moving to a place where, say, with W first, we're expecting 10,000 microlensing events. We're expecting thousands of planets. We don't want to look at each of them with the same, loving care that we give every microlensing event now. We want to have a box. We want to put microlensing events in one side of the box, and we want to get information about planets and planet statistics out the other side. But this event demonstrates clearly that your box has to be more complicated than fit planets to your data. You have to also be aware of the different kinds of microlensing effects that can mimic planetary signals. And so this is one of them. It's very similar to a degeneracy proposed by Gaudy, but in that case, he was thinking about a broad microlensing event with a very short perturbation superposed on each other. And in this case, it's a lot more messed up than we expected to get from binary sources. And so, this is just one of the things we need to be keeping in our mind as we go forward to these mass analyses of microlensing planets. Another thing that Jungiel found is this 1003. And, it looks like it should be a classic microlensing binary. Beautiful, microlensing stellar binary. But if you look in detail at the caustic exit, you can see the KMT data resolve actually two different caustic exits, which is kind of a problem because a caustic is a closed curve. And so if you go in, you can go out, but you can only do those things once. You don't get to do them twice. And so it's clearly more complicated than just a simple binary lens. And so Jungiel fit this with a triple lens model. In this case, the first caustic exit is actually due to passing by an interior caustic structure due to a planet. So this system, for the triple lens model, you've got an M dwarf, you've got a brown dwarf, and then you've got a Neptune mass planet. So great, more planets, I like that. But he found a competing model, which is the binary lens, binary source model, where you've got two lens stars and two source stars. And you could figure this out if you had data on the caustic entrance. But from KMTnet, we didn't have data from the caustic entrance, right? So the triple lens model should have only one caustic entrance because that second feature is just an interior caustic structure. So you go in and you come out. If it's a binary source model, then you have two caustic entrances. And from KMTnet, this is all the data we had. The Ogle data are shown here in the green as well, but it didn't help us. But I did some detective work, and I realized that our collaborators, the MOA collaboration, which is based in New Zealand, so at a slightly different longitude, ought to have data on this event. And so just last week, I wrote to them, and they finally sent us their data on this event. And it clearly shows that the binary source, binary lens model is the correct one. So you see two caustic entrances from MOA data, and two caustic exits, which is the correct pairing of things if you have a closed structure. And so what we see is that we have this caustic due to the binary lens, and then we have these two sources crossing across this caustic, producing this beautiful and unexpected structure. And so you're getting near the end, but with the combination of these two projects, the Spitzer project to measure microlens parallaxes, and KMTnet, which is this large survey with a very high cadence covering many microlensing events, we're getting to we're exploring new frontiers in microlensing. So with Spitzer, we realized that we could use microlensing to study the galactic distribution of planets. Right? And so 1/3 of planets that we discovered with microlensing, we expect to be in the bulge. And if we can measure parallaxes for them, then we can figure out that they are in the bulge. KMTNet is showing these new complex microlensing systems with triple lenses, with binary sources and binary lenses in combination. Just things that, are theoretically possible, but never really expected to see. And then we're also able to do these direct tests of microlensing techniques. And so, that's what science is. You have an observation, you make a prediction, and then you test that prediction and see if it works. And so Ingu did that with this observation of this Spitzer binary. And so going forward and looking forward to W first, all of this is feeding into our thinking about W first. And so this morning at the ICC luncheon, I talked about non-microlensing science with W-first microlensing data. But of course, the point of taking this data is to observe microlensing planets. This is a simulation of what a microlensing planet should look like with W-first. This planet is a Mercury mass planet detected by W-first. Right. Beautiful thing. W-first should also expect to detect free-floating planets, planets without host stars, because you're not worried about their light. You don't need to detect light, you just need to detect their gravity. And so this is what a free-floating Mars mass planet would look like with W-first. And so W-first is going to revolutionize the field again, right? So with the survey plus follow-up of microlensing, we were really only sensitive to gas giant planets. But with things like KMTNet, we're pushing down in mass and out in separation, and we're getting into sort of the Earth mass planet regime. W-first is expected to go all the way down to planets with a mass of Ganymede, and to cover this huge range of separations. And here the separations are scaled by snowline. And the reason is because microlensing is primarily sensitive to M dwarfs, because they're the most common stars in the galaxy, whereas RVs and Kepler focus mostly on G dwarfs. And so by scaling to the snowline, you're talking about similar environments around these different mass stars. And so W-first is hugely sensitive to the planets beyond the snowline. And so hugely sensitive to probing what's going on in this region where giant planets are supposed to be forming. And so all of this stuff that we're doing now with Spitzer and KMTNet I think is super cool all by itself, but it's also helping to inform and planning for W-first to help us consider the different things that W-first might also be able to observe, and to help us design that box so that we can put W-first light curves in one side and get answers about planet demographics out the other. And so that's all I have to say today. So thank you.
It's hard to believe there aren't a lot of questions. We have questions for us, Gary.
Well, it's very impressive what you get with the combination of these two sites, the Earth and Spitzer, and presumably you'll be doing the same with W-first and Earth-based observations, right?
Maybe.
Maybe.
So it's different. So one of the key elements between the Earth and Spitzer is they're separated by 1 AU.
Right.
W-first will go to L2, so the separation will be much smaller.
Well, this is leading to my question. And
Right.
my actual question is, how much additional benefit, how much additional information comes from a third line of sight? In other words, how much value is added if one were to propose SMEX or a mid-X to coincide with the time scale of W-first that would be Earth trailing and provide quite a large separation, and then you have 3 lines of sight?
Okay, so the reason I'm thinking about this is it depends a little bit. Spacecraft have their particular viewing angles. And so the W-first viewing angle is set so that it observes a quadrature in March. And so I'm not sure what the practicalities of that are in terms of getting something in Earth trailing orbit that can also observe towards the bulge at the same time as W-first. But there is really interesting science to be done with that, because one of the things that you might want to do is you might want to probe these free-floating planets. And so the thing in microlensing is that what you're measuring is you're measuring the time scale. And that time scale depends on your proper motion, it depends on your mass, and it depends on your distance. And so when you have a very short time scale thing, it might be a free-floating planet because it has a very small mass, but it also just might be something that's moving super fast. And so the way to figure that out is to measure parallax with something like you proposed. So that is an interesting idea.
Charles.
So at what point does your photometry get good enough that you can deduce the parallax reliably just from the motion of the Earth during the event, which we've done successfully for very long duration events?
Right. So we expect to do that for many W first events. I don't know the exact fraction, but I know it won't work for free-floating planets.
No.
Right. So I don't quite know the answer to that. Generally now we're limited to things with 50 days is a good separation. So I suspect we could get down to more typical events, which are 20 days with W first precision photometry.
So in all of this modeling, there is also the question of the transverse velocity of the lens and the source.
Mm-hmm.
So what do? Do you solve for that, or are you assuming some standard probability distribution?
So you solve everything in the frame of the Einstein ring. And so you solve everything relative to the size of the Einstein ring. And that's, so you're measuring this time scale, which is the number of days to cross the Einstein ring. And then once you've measured the Einstein ring, if you measure the Einstein ring size, then you're measuring the relative proper motion between the two objects, but not their velocity. Relative proper.
But if there is just a simple magnification curve,
Mm-hmm.
no planets, no nothing,
Right.
no parallax, how do you analyze something like that?
So then you just analyze it scale to the Einstein ring. So it's
Gotcha.
just, time of the peak, duration of the peak, impact parameter as a fraction of the Einstein ring. Just those three parameters.
Right, you don't get a mass.
Right. You don't, which is why we need parallax.
Igor.
When we do stellar population modeling of galaxies, we have a sort of three-parameter, arbitrary, I would say, that is called a fraction of closed binaries. It's used for different, relativistic systems, computation of SN1A frequencies, and so on and so forth. But obviously, at the low mass end, you must have those binaries made of tiny red dwarf stars. Do you have any constraints on this thing from your observations? Because you have hundreds of events, you must, if it's 5%, as we think, well, as people think in stellar population modeling, you should be able to see them. I'm talking about very close binaries, like days of periods.
So maybe you and Bill could say more about this, but microlensing has previously found these very tight, very low mass brown dwarf binaries. The only thing, so we know we can detect them. The thing that we don't know yet is what fraction of them out of all binaries they are. So that's the question, how to do the population statistics, not just finding objects, but figure out what the fraction of the population is, and we haven't done that yet, but we could do that in the future. And so it's one of the things that we're thinking about.
Steve.
Was there a Kepler microlensing campaign at some point?
Yes,
What
last
happened?
year. What happened, first Kepler broke, and then it was fixed. And so that was campaign 9, and so it was somewhat shorter than expected. But it happened, and there's data, and I'm expecting to hear an update about the status of the data reduction next week at the microlensing meeting.
Sure.
I'm just raising my hand for Andrew.
Oh,
Raising his hand.
Andrew. Sorry, I didn't see you.
I was wondering, when you have these events that have binary or triple source stars, are those just superpositions of the events that you would see from a single source star? Or is there some higher order effect?
When it's source stars, it's a superposition. When it's lens stars, it's messed up.
No more hidden questions up there? Oh, I'm sorry.
Do you gain any extra information about having the two different wavelengths for the observation? Do you extra information?
If it's a binary source, you get information from two different wavelengths. So now that we know microlensing exists and is a real thing, we no longer have to prove that it's achromatic, which was true in the early days, to prove that it was achromatic and therefore microlensing. Now the thing that we're thinking about is to what extent does multiple bands help us, because we're seeing these binary source events. And so if you have a binary source event degenerate with some other like binary lens model, then if the two components of the binary source have different colors, you're going to see a color effect, a color-dependent effect in your light curve, as the two things are magnified by different amounts. And so we're starting to think about maybe that we should go back to taking color data, take more color data, to figure that out. That's one of the things that Junkel tested with this binary source, binary lens model, was what was going on with the colors. And had to show that the two source stars would actually lie in the same isochrone.
So a follow-up question, are there filter changes in the KMT-net program?
There are. So we're taking V-band, the idea is that the most V-band data will come from CTIO, but there's at least 1 point per night from SAAO, which is in South Africa. So KMT-net has the 3 sites. One at CTIO, which is the best site, being in Chile. SAAO, which is in South Africa, and then SSO, which is the Australia site, which is less good. And so the emphasis is on taking more V-band data from the better sites, because they lose less due to weather issues. Yeah.
Joey, last question.
So I know that if you were to wait a long enough time, right, the lens would eventually separate from the source.
Yeah.
And you could actually detect the planet through other mechanisms down the line, say radio velocity measurements. Has that been done? Is it going to be done? Is there prospects for that going forward with W first?
Right.
And is there any value to that?
So, we have detected a microlensing system with radial velocity. That's a project I worked on with John. But in that case, it was a binary system. And that was one of the brightest binaries that we have in microlensing. It was 17th magnitude. And so there's very little hope following up planets around microlensing events with methods like radial velocity.
Okay, Jennifer will be visiting with us for a few years, I hope. You know where to find her? Let's thank our speaker again.